Introduction echoes from the dawn of time. In the vast silence of the cosmos, there exists a whisper, faint, persistent, and ancient. It is not a sound we can hear with our ears, but a radiation we can detect with our instruments. Quiet signal, known as the cosmic microwave background, or CMB, is the oldest light in the universe. A faint afterglow left behind from the fiery birth of everything we know over 13 billion years ago. The universe erupted into existence in the event we call the Big Bang. In those first moments, 'twas a hot, dense, and opaque fog of particles and energy. But as it expanded and cooled, a transformation occurred. At around 380,000 years old, the universe became transparent. Light was finally free to travel across space, and that light has been journeying ever since, stretched by the expansion of space itself into microwave wavelengths. This ancient light, still present in every direction we look, holds the clues to our cosmic origins. The cosmic microwave background is more than a relic. It is a cosmic map, etched with subtle patterns, tiny fluctuations in temperature and density that reveal the seeds of galaxies, stars, and planets. It tells us about the composition, structure, and fate of the universe. It is one of the most important discoveries in the history of cosmology. Yet it remains a gentle mystery that continues to challenge and inspire scientists today. In this audiobook, we will journey into the heart of this cosmic echo. We will explore its discovery, its implications, and the incredible technologies used to observe it. We will uncover what the CMB reveals about dark matter, dark energy, inflation, and the shape of the cosmos itself. With each chapter, we will peel back another layer of the universe's earliest story. So find a quiet space. Let your curiosity drift through time and space, and join us as we unveil the mysteries of the cosmic microwave background. Chapter 1: The Discovery That Changed Cosmology. In the early 1960s, two radio engineers, Arno Penzias and Robert Wilson, were not searching for the origin of the universe. They were simply trying to eliminate noise from a large horn-shaped antenna at Bell Telephone Laboratories in New Jersey. The antenna, originally designed for satellite communication, was picking up a persistent background hiss that seemed to come from every direction in the sky. They tried everything to get rid of it, even removing nesting pigeons and cleaning out their droppings. But the noise remained. What they had stumbled upon, unknowingly, was the faint whisper of the cosmos itself, relic, radiation from the Big Bang, stretched into the microwave portion of the spectrum. This signal, later identified as the cosmic microwave background, CMB, would become one of the most important discoveries in modern science. It offered tangible evidence that the universe had a hot, dense beginning. Meanwhile, just 30 miles away at Princeton University, A group of physicists, led by Robert Dicke, had been working on a theoretical prediction. Based on the Big Bang model, they expected the early universe to leave behind a residual glow-form of thermal radiation that would still permeate the universe. They were preparing to build an instrument to search for it when they received a call from Penzias and Wilson. The engineers described the persistent noise, and the Princeton group instantly realized what had been found. As Dicke famously said after hanging up the phone, "Well, boys, we've been scooped." The discovery, published jointly in 1965, was modest in tone, but monumental in impact. Until then, the steady-state theory had competed with the Big Bang as a model for the universe. The steady-state model suggested that the universe had no beginning and no end, simply existed, constantly creating new matter as it expanded. But the CMB was a glowing fingerprint from a time when the universe was much younger and hotter. Something the steady-state model could not explain. The radiation was remarkably uniform across the sky, with only the tiniest variations, parts in 100,000. This isotropy aligned with the Big Bang prediction that the early universe was nearly homogeneous, with minor fluctuations that would eventually grow into stars and galaxies. This tiny unevenness, preserved in the CMB, would become the blueprint of cosmic structure over time. The discovery of the CMB would earn Penzias and Wilson the Nobel Prize in Physics in 1978. But beyond accolades, it marked the dawn of precision cosmology, the use of detailed measurements to unlock the history and fate of the universe. The faint microwave glow is now studied with incredible accuracy by satellites like COBE, WAMAP, and Planck, revealing deeper insights with each generation. It's poetic to think that the echo of creation, born in fire and fury, ended up being heard not in a grand observatory, but in a quiet lab where two engineers were just trying to fix a noisy antenna. Their curiosity and patience opened a window into the past, a time when the universe was only hundreds of thousands of years old, still glowing from its birth. The cosmic microwave background is not just a discovery. It is a messenger from the ancient universe. Its presence affirms that we are part of a cosmic story that began long ago. Chapter 2: A Glimpse into the Infant Universe. Imagine the universe as a newborn, not yet a minute old. It is unimaginably hot and dense, a swirling soup of fundamental particles, protons, electrons, photons. In this primordial fireball, light cannot travel freely. Photons, the particles of light, are constantly scattered by the charged particles in the plasma, like headlights trapped in dense fog. The universe is bright, but opaque radiation and matter are locked together in a chaotic dance For hundreds of thousands of years, this seething cosmos continues to expand and cool. At first, temperatures are so high that even atomic nuclei cannot capture electrons. They are immediately knocked loose by energetic photons. But as the universe grows older, the energy begins to drop. Finally, at around 380,000 years after the Big Bang, a threshold is crossed. The temperature dips to about 3,000 Kelvin, cool enough for protons and electrons to combine into neutral hydrogen atoms. This transformation is called recombination, though it is really the first time atoms have ever formed. Suddenly, the fog lifts. Photons, no longer constantly colliding with free electrons, are released. They begin a long, uninterrupted journey through space. These first free-traveling photons are what we now observe as the cosmic microwave background. The universe has become transparent, and for the first time, light can roam freely through the cosmos. This moment is often referred to as the surface of last scattering kind of cosmic photosphere. Just as the surface of the sun is the layer from which sunlight escapes into space, the last scattering surface is the layer from which these ancient photons were last scattered before heading toward us. It is not a surface in the usual sense, but a vast, spherical shell surrounding us, marking the limit of our observable view into the past. What we see in the CMB is a picture of the universe frozen in time, an image of what it looked like at that critical moment. The photons have been stretched by cosmic expansion over billions of years, shifting their wavelengths into the microwave range. They now appear as a nearly uniform glow in all directions, with tiny temperature differences mere millions of a degree that correspond to subtle variations in density and composition. These anisotropies, as scientists call them, are the fingerprints of the infant cosmos. They are the seeds of cosmic structure, where slightly denser regions would eventually collapse under gravity to form galaxies and clusters. Less dense regions would expand, creating the vast cosmic voids we observe today. It is from these faint imprints that a universe's large-scale web would grow. Studying the CMB is like examining a baby photo of the universe, one that reveals its birthmarks, imperfections, and earliest tendencies. From it, we can infer not only how the universe looked in its youth, but also its composition. How much of it was ordinary matter, dark matter, and radiation. We can also begin to understand its geometry and its fate. Incredibly, this snapshot from the early universe is still detectable with delicate instruments more than 13 billion years later. Every time we look at the sky with a sensitive microwave detector, we are gazing at the afterglow of creation. A cosmic time capsule traveling at the speed of light. The cosmic microwave background is not just ancient light is a portal. Through its faint glow, we gain access to the universe as it once was, peering through layers of time, unraveling the story of everything from galaxies to gravity. Chapter 3: The Physics Behind the Glow. The cosmic microwave background may seem like a simple glow uniform, faint and cold, but hidden within it lies a rich tapestry of physical processes that shaped the cosmos. To truly appreciate what we're seeing when we observe the CMB, we must explore the physics that governs this ancient light and how it came to be preserved. Across billions of years, at the core of the CMB's origin is a profound transition, the moment when light decoupled from matter. In the hot, dense, early universe, photons, particles of light, were constantly interacting with free electrons through a process known as Thomson's scattering. This created a state of thermal equilibrium. Matter and radiation were locked in a feedback loop where no photon could travel very far without being absorbed or scattered. But as the universe expanded, it cooled. Expansion, in the context of the cosmos, is not matter moving through space, it is space itself stretching, which causes the energy of particles, including photons, to drop. Eventually, the temperature fell below the ionization point of hydrogen, allowing protons and electrons to combine into neutral atoms. This sudden drop in free electrons broke the cycle of scattering. Light was now free to travel without obstruction. And that light, the decoupled photons, is what we see as the CMB. The radiation at that moment followed a blackbody spectrum, a perfect curve determined solely by temperature. What is astonishing is that even today, after traveling for over 13 billion years, the CMB still retains a nearly perfect blackbody profile. This remarkable preservation tells us that the universe has remained largely transparent and homogeneous on vast scales since the moment of recombination. But while the average temperature of the CMB today is a chilly 2.725 Kelvin, it wasn't always so. The cooling is a direct consequence of the universe's expansion. As space stretches, it increases the wavelength of photons, a phenomenon known as cosmological redshift. Photons that were once in the visible or infrared range have been elongated into the microwave spectrum, turning a once blazing glow into a barely perceptible hum. What makes this radiation even more valuable to cosmologists is that it acts as a cosmic thermometer and ruler. The slight variations in its temperature on the order of microkelvins carry information about early fluctuations in the density of matter. These fluctuations, generated by quantum processes during the earliest moments of the universe, were amplified by gravitational instability and laid the groundwork for all future structure, stars, galaxies, and cosmic filaments. The physics of sound also plays a role here. Before recombination, the early universe behaved like a plasma fluid, where matter and radiation were tightly coupled. In this fluid, pressure and gravity created oscillations or sound waves traveling through the primordial plasma. Oscillations left imprints in the CMB in the form of acoustic peaks patterns in the temperature fluctuations that correspond to inquestine. They correspond to different scales of compression. By studying these peaks, scientists can extract an incredible amount of information. The amount of dark matter, the geometry of the universe, and even the rate of cosmic expansion. To read the CMB is to understand how light, matter, and gravity interacted in a delicate cosmic ballet. It reveals the fundamental parameters that describe our universe, much like a DNA sequence reveals the code of life. And yet, this ancient radiation is remarkably silent. It does not flicker, pulse, or change. It simply persists, an omnipresent backdrop to the stars. It is the canvas on which the entire story of cosmic evolution is painted, unchanging but deeply informative in its faint whispers. The CMB tells us that the universe is governed by laws logent, consistent, and universal. To general relativity, the physics behind this glow connects the very small with the very large, illuminating the invisible threads that bind all things together. Chapter 4: Tiny Fluctuations. Grand structures. When we gaze into the cosmic microwave background, we're not seeing a perfectly smooth glow. Instead, there are minute ripples, tiny temperature variations scattered across the sky. Mere millions of a degree might seem insignificant at first glance, but they are the fingerprints of creation itself, the subtle marks left by the primordial forces that would eventually sculpt the vast and complex universe we see today. These temperature fluctuations are known as anisotropies, and they are not random. They reflect slight variations in the density of matter and energy in the early universe regions where gravity was just beginning to take hold, tugging ever so gently on particles, drawing them together. Over billions of years, these denser spots would grow, forming the cosmic web of galaxies, stars, clusters, and voids that now spans across space. The origins of these fluctuations can be traced back to the inflationary Eureka moment, just fractions of a second after the Big Bang, when the universe expanded exponentially. During this burst of rapid inflation, quantum fluctuations, normally confined to microscopic scales, were stretched to cosmic proportions. These quantum wrinkles became the seeds of large-scale structure, frozen into the fabric of spectromy. As the universe cooled and the cosmic microwave background formed, these differences in density were encoded into the radiation. Areas of slightly higher density appeared a bit warmer. Lower density regions slightly cooler. These temperature maps are like ancient photographs, capturing a snapshot of the earliest matter distribution to visualize the scale of these fluctuations. Imagine that the universe is a nearly perfect sphere, but with the texture of an orange peel, bumpy and irregular at a minuscule level. These irregularities, though subtle, were crucial. Gravity would have had no foothold, and matter would have remained evenly spread. There would be no stars, no galaxies, no planets, and no life. The acoustic waves that traveled through the early plasma also left their signature in the distribution of these fluctuations. Like ripples in a pond, these sound waves formed concentric patterns that we can still detect today in the form of acoustic peaks in the CMB power spectrum. Each peak corresponds to a different scale of oscillation, providing a precise tool for cosmologists to measure the composition of the universe. These small ripples carry immense information. By analyzing their size, distribution, and amplitude, scientists have determined that the universe is made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB also confirms that space is geometrically flat, that the universe is expanding, and that its fate is intimately tied to the invisible forces we are only beginning to understand, perhaps. What is most humbling is that everything we know, the galaxies, the stars, the atoms in our bodies, originated from these tiny primordial ripples. The grand architecture of the cosmos was sculpted from quantum fluctuations amplified by inflation, shaped by gravity, and recorded in light dot. In this way, the cosmic microwave background is not merely a relic. It is a bridge connecting the quantum realm to the cosmic. It shows us how the smallest disturbances in an early, chaotic universe gave rise to patterns that stretch across billions of light years, tiny though they may be. These fluctuations are the blueprint of all structure. In their faint contrast, we see the first hints of everything that was to command entire universe, drawn from the most delicate of beginnings. Chapter 5: The Era of Recombination. Long before stars ignited and galaxies spiraled into being, the universe was a glowing fogging ocean of searing heat and light, where matter and radiation were tightly entwined. It was a place of intense chaos, where photons bounced relentlessly between particles, unable to travel far without being scattered. For hundreds of thousands of years after the Big Bang, this early universe remained opaque, filled with high-energy particles and radiation, locked in constant interaction. But around 380,000 years after the Big Bang, a dramatic shift occurred, one that would forever change the cosmos and allow light to begin its journey across time and space. This transformation is known as the era of recombination, a period when the universe cooled just enough to permit electrons and protons to unite, forming the first stable atoms of hydrogen. At first glance, the term recombination might seem misleading. There had been no previous combination of these particles. This was their very first union. But in physics, the term endures, a nod to processes more familiar in laboratory plasmas. Still, what occurred was revolutionary. As temperatures fell below approximately 3000 Kelvin, the thermal energy of photons became too weak to prevent the formation of neutral hydrogen. Suddenly, electrons were no longer ripped from protons by high-energy radiation. The fog began to clear. This moment of clarity marked the decoupling of matter and radiation. Until then, photons had been trapped, scattered endlessly by free electrons. But with the birth of neutral atoms, the universe became transparent. Photons could now move freely, unimpeded by constant collisions. These newly liberated particles of light began to stream across the cosmos in every direction. And they're still traveling today. We detect them as the cosmic microwave background, the cooled remnants of the first light. What was once a brilliant, high-frequency blaze is now a gentle hum, stretched by billions of years of cosmic expansion into the microwave part of the spectrum. And although its temperature today hovers just above absolute 2.725 Kelvin, to be exact, it carries within it an extraordinary message from the past. This message is not only one of age, but of structure and formation. During recombination, subtle variations in density across the early universe were imprinted onto this newly transparent light. These tiny fluctuations are visible in the CMB as slight differences in temperature anisotropies, and they mark regions where matter was either slightly denser or more rarefied than average. The denser regions, just slightly warmer, had a bit more gravitational pull. Over immense spans of time, those slight differences would snowball, attracting more matter and evolving into galaxies, stars, and eventually planetary systems. The less dense regions, a bit cooler, would become the vast voids between clusters of galaxies. This era also gave rise to what scientists call the last scattering surface, the metaphorical shell from which the photons we now detect were last scattered before flying freely through space. It forms a kind of boundary of the observable universe, a spherical wall of ancient light surrounding us from all directions, giving us a glimpse into the deepest past. But recombination wasn't instantaneous. It was a gradual process occurring over tens of thousands of years. As the universe expanded and cooled further, more and more atoms formed, and the scattering of photons diminished steadily. The result is not a sharply defined surface, but rather a fuzzy boundary, a transitional zone where the fog thinned enough for light to escape. Even after recombinations, the universe remained dark for a long time, with no stars yet formed and the background glow cooling into obscurity. This period is known as the cosmic dark ages. Light had been set free, but the sources of new light stars and galaxies had yet to emerge. It would take several hundred million years for gravity to gather matter into the first luminous objects. Still, the light from recombination remains one of the most profound tools we have. Like a photograph of a newborn cosmos, it preserves conditions with incredible clarity. The patterns frozen into this light allow scientists to test theories of gravity, quantum mechanics, and the large-scale evolution of the universe with remarkable precision. The era of recombination was not simply a cooling. It was a threshold, a line crossed in the grand narrative of existence. Before it, the cosmos was a furnace of formless energy. After it, the stage was set for structure, for complexity, for life. It marked the beginning of the universe's transformation, from chaos to cosmos, and every night, that ancient light still whispers its tale gently across the vast dark, reminding us of the moment when the universe first opened its eyes. Chapter 6. The Sound Waves of the Cosmos. Before the universe became transparent, before light broke free to traverse space, an extraordinary music played through the fabric of the cosmos. Though we cannot hear it with our ears, its echoes are written into the cosmic microwave background. This ancient harmony was not made of wind or strings, but of matter and radiation, vibrating together in the dense, hot plasma of the early universe. These were the sound waves of the cosmos, and they would shape the very structure of everything to come in the primordial universe. Before the era of recombination, the cosmos was filled with a dense, hot plasma fluid of tightly coupled photons and baryons, protons, and neutrons. In this fluid, two opposing forces struggled for dominance. On one side, gravity tried to draw matter together, creating dense regions. On the other, radiation pressure from photons pushed outward, resisting compression. This constant tension between pull and push generated oscillations, ripples of compression and rarefaction, propagating through the early universe like sound waves through air. These ripples are known as baryon acoustic oscillations. They were created when an initial overdensity caused by quantum fluctuations during inflation triggered gravity to pull matter inward. As the region compressed, photon pressure pushed back, causing the matter to bounce outward again. This process repeated, setting up waves in the plasma. Each wave moved outward until the moment of recombination, when the photons decoupled and the pressure driving the oscillations vanished. The result was a series of frozen patterns imprinted into both the matter distribution and the CMB. These patterns are visible today as alternating bands of slightly hotter and cooler regions in the cosmic microwave background. By mapping the angular scale of these fluctuations, scientists can read the acoustic signature of the early universe. The most prominent of these patterns is the first acoustic peak, corresponding to the largest compression wave that had just enough time to form before recombination occurred. Each acoustic peak in the CMB power spectrum carries vital information about the universe's contents and geometry. The height and spacing of the peaks reveal how much matter, both visible and dark, was present, how much radiation, and how tightly the universe was curved. For instance, the location of the first peak strongly supports a flat universe. In line with predictions from inflationary theory, what's remarkable is that these sound waves generated in a hot plasma more than 13 billion years ago still guide our understanding of cosmic structure. In fact, the same oscillatory pattern exists in the large-scale distribution of galaxies we observe today. Over time, the pressure-driven waves left behind faint imprints on the way galaxies clustered. Cosmic ruler, about 500 million light-years in length. By measuring this scale at different epochs, cosmologists can track the expansion rate of the universe and probe the effects of dark energy. So, in a sense, the early universe sang a note deep, primordial, and vast. That note has not vanished. It resonates still in the temperature maps of the sky and in the galaxy surveys that stretch across billions of light-years. It is not music in the human sense, but its rhythm and structure are encoded in the very geometry of space. These waves are more than a relic. They represent a link between microphysics and the cosmic order, a connection between tiny quantum ripples and the grand orchestration of galaxies and voids. They show us that the universe's earliest moments were not silent or chaotic, but dynamic and harmonious, fluid composition of matter and energy finding equilibrium in an expanding sea of possibilities. The cosmic microwave background, with its subtle ripples and quiet textures, holds the final note of that long-dissipated sound. When we study it, we are listening to the echoes of a time when the universe pulsed with rhythm, pressure, and force. And from those waves came structure. From structure came stars, and from stars came us. Chapter 7. From Cope to Planck. Eyes on the early cosmos. The story of humanity's exploration of the cosmic microwave background is one of ever-increasing precision, technological innovation, and deepening understanding. From the first accidental detection in the 1960s to the detailed maps produced in the 21st century, a series of ambitious space missions have progressively unveiled the secrets hidden in this faint glow. The journey began with the COBE satellite, the Cosmic Background Explorer launched by NASA in 1989. COBE was the first instrument designed specifically to study the CMB. Its measurements confirmed that the radiation perfectly matched a black body spectrum with astonishing precision, reinforcing the Big Bang model. More importantly, COBE detected the first subtle anisotropist, the tiny temperature variations that encode the universe's early structure. These initial detections were groundbreaking, but limited in resolution. The temperature differences measured were on the scale of 1 part in 100,000. The images were blurry by today's standards, but they paved a way for future missions, building on COBE's legacy. NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001. WMAP provided a more detailed, high-resolution, full-sky map of the CMB anisotropies, measuring temperature differences with unprecedented accuracy. Its data allowed cosmologists to refine estimates of the universe's age, composition, and expansion rate. For example, WMAP pinned down the universe's age at about 13.77 billion years and confirmed the proportions of dark matter and dark energy with remarkable precision. WMAP's success ushered in an era of precision cosmology, where theoretical models and observations converged to paint a consistent picture of the cosmos. But even WMAP had its limits. Enter the Planck satellite. Launched by the European Space Agency in 2009, Planck represented the pinnacle of CMB observations to date. Equipped with instruments sensitive to both temperature and polarization across multiple frequencies, its maps revealed anisotropies on finer angular scales than ever before. And its data continue to be the gold standard in cosmology. Planck's measurements provided tighter constraints on cosmological parameters and revealed subtle features in the CMB, such as the polarization patterns connected to gravitational waves and the early universe's inflationary epoch. It also helped refine models of foreground emissions noise from our own galaxy that obscures the CMB signal. Thanks to these missions, our understanding of the universe's origins and evolution has become more precise and nuanced. Each satellite was a new set of eyes, peeling back layers of cosmic history, revealing the structure of the universe at scales unimaginable just decades ago. But the journey is far from over. New experiments, both on the ground and in space, aim to measure the CMB with even greater sensitivity, searching for elusive signals that could confirm inflation. Detect primordial gravitational waves or uncover new physics beyond our current theories. The story of exploring the cosmic microwave background is a testament to human curiosity and ingenuity. From two engineers struggling with a noisy antenna to sophisticated spacecraft mapping the oldest light in the universe, it is a journey that connects us to the dawn of time and the mysteries that still await. Chapter 8: Polarization, a new layer of clues when we think of the cosmic microwave background. We often imagine it as a faint, uniform glow surrounding us in all directions. But this ancient light carries more than just temperature information. It is also polarized, meaning its waves oscillate preferentially along certain directions. This subtle polarization is a rich source of information, an additional layer of cosmic clues. Hidden within the oldest light, polarization occurs when photons scatter off free electrons, especially in regions where the radiation field has an anisotropicnon uniform distribution. In the early universe, just before and during recombination, the tight coupling between photons and electrons led to such conditions. As photons decoupled and traveled freely, their polarization patterns were frozen in place, providing a snapshot of the physical processes at that time. Scientists classify CMB polarization into two distinct types: E modes and B modes. E modes are patterns with radio or tangential symmetry around cold and hot spots, and they were first detected in the early 2000s. They confirm much of what we understand about density, fluctuations, and the physics of recombination. B modes, on the other hand, are a swirling, curl-like pattern. Their detection is more challenging and tantalizing because they could be the signature of primordial gravitational waves, ripples in space-time generated during cosmic inflation. Such waves would have left their imprint on the CMB polarization, twisting it in this unique way. The hunt for B mode has driven a global effort, inspiring sensitive experiments like BICEP, POLARBER, and the upcoming satellite missions dedicated to CMB polarization. Detecting these patterns would not only provide direct evidence for inflation, but also offer a glimpse into the earliest instance of the universe, mere fractions of a second after the Big Bang. Moreover, polarization data help refine our understanding of other cosmological parameters. They improve measurements of the universe's reionization epocha. Later period, when the first stars reionized, the intergalactic media band provide insights into the behavior of dark matter and neutrinos. But observing CMB polarization is no simple task. Foreground emissions from dust within our own Milky Way galaxy can mimic or obscure the signals researchers seek. Separating this cosmic noise from the genuine primordial patterns requires meticulous analysis and multi-frequency observations. Despite these challenges, polarization studies have already transformed cosmology. They complement temperature measurements, breaking degeneracies and tightening constraints on models of the early universe. Polarization is a new dimension in our exploration, one that enriches the cosmic story told by the ancient light, taught in every polarized photon from the cosmic microwave background. There is a silent testament to the forces and events that shaped everything we see today. Through it, we are not only witnesses to the universe's birth, but also to the dynamic processes that sculpted its earliest moments. The CMB's polarization is a whisper from the dawn of time, revealing a cosmos more intricate and profound than we ever imagined. Chapter 9: Echoes of Inflation. A fraction of a second after the Big Bang, the universe underwent a breathtakingly rapid expansion phenomenon known as cosmic inflation. This event stretched space itself at speeds faster than light. These primordial ripples became the seeds for the large-scale structure of the cosmos. We observe today, inflation elegantly explains several puzzling aspects of the universe. It accounts for the observed homogeneity and isotropy. Why the cosmos looks nearly the same in every direction. It also provides a mechanism for generating the initial fluctuations that later grew into galaxies and clusters. But inflation, by its nature, is difficult to observe directly. Its effects are subtle and encoded deep within the cosmic microwave. Background: the CMB acts as a cosmic record of inflation's aftermath. The tiny temperature anisotropies we detect are the magnified imprints of quantum fluctuations stretched across the infant universe. These fluctuations follow a nearly scaling variant power spectrum, meaning similar patterns appear on many scales, matching inflationary predictions with remarkable accuracy. But inflation leaves more than just temperature patterns. The very fabric of space-time would have been shaken by primordial gravitational waves. Ripples of gravity generated during inflation's violent expansion. These waves would imprint a distinct signature in the beam mode polarization of the CMB, a swirling pattern that researchers continue to search for. Detecting these primordial gravitational waves would be a groundbreaking confirmation of inflation theory. It would open a window into physics at energy scales far beyond the reach of any particle accelerator, offering clues about quantum gravity and the earliest moments of time, although direct evidence remains elusive. The CMB data collected by Planck and other missions constrain inflationary models, ruling out many possibilities and guiding theorists toward more precise descriptions. Some models predict subtle, non-Gaussianite small deviations from the expected statistical patterns that scientists are actively searching for. Inflation remains one of the most profound ideas in modern cosmology. It transforms our understanding from a simple, expanding universe into one that emerged from a dynamic, quantum-driven phase. The echoes of inflation resonate in the ancient light, whispering secrets about the origin of space, time, and matter through the cosmic microwave background. We peer beyond the veil of time, glimpsing the turbulent birth of the cosmos and the forces that shaped all that followed. Inflation's echoes remind us that our universe is not static or accidental, but born from processes both subtle and spectacular. Chapter 10: The Cold Spot Enigma. As scientists mapped the cosmic microwave background in exquisite detail, they uncovered a puzzling feature: a region in the sky significantly colder than its surroundings. Known simply as the cold spot, this anomaly stands out like a dark blot on an otherwise nearly uniform canvas, challenging cosmologists to explain its origin and meaning. The cold spot spans roughly 5 degrees across the sky, enormous scale considering the vast distances involved. Its temperature is about 70 microkelvins cooler than the average CMB temperature, a deviation far larger than expected from random fluctuations predicted by the standard cosmological model. Several hypotheses have emerged to explain this mysterious chill. One possibility is that the cold spot is a statistical fluke, a rare but not impossible chance occurrence in the cosmic variance of the CMB. After all, when surveying the entire sky, unusual spots can appear simply by coincidence. However, other explanations hint at profound implications for cosmology. Some suggest the cold spot is caused by a supervoid, immense, underdense region in the large-scale structure of the universe. Via the integrated Saxe-Wolf effect, appearing colder when they reach us. Surveys have detected large-scale voids in that direction, but whether they fully explain the cold spot remains debated. More speculative theories propose that the cold spot could be a signature of exotic physics, perhaps evidence of multiverse collisions where our universe interacted with another bubble universe during inflation. Such interactions might leave imprints in the CMB like scars from cosmic encounters beyond our observable horizon. Others have considered the possibility of anisotropic or non-standard cosmologies, suggesting that the universe might have large-scale features or topologies not accounted for in the standard model. The cold spot could then be a hint toward a more complex cosmic architecture. Despite intensive study, the cold spot remains enigmatic. Its existence challenges the idea of a perfectly Gaussian and statistically uniform CMB, prompting ongoing investigations and new observational campaigns. Interestingly, the cold spot also raises philosophical questions about the nature of randomness and order in the universe. Is it a mere coincidence or a meaningful cosmic clue? Could it reveal new physics or the limitations of our current theories? Whatever its origin, the cold spot is a reminder that the cosmic microwave background is not just a uniform backdrop, but a textured, dynamic storybook. It contains surprises and puzzles that continue to inspire wonder and curiosity. As we push the boundaries of observation and theory, the cold spot stands as a silent sentinel, inviting us to look deeper and question the cosmic narrative. It reminds us that the universe, vast and ancient, still holds mysteries waiting to be unveiled. Chapter 11. Dark Matter's Silent Influence. Though invisible to our eyes and undetectable by ordinary light, dark matter exerts a profound influence on the universe and on the cosmic microwave background itself. This mysterious form of matter, making up roughly 27% of the universe's total mass energy content, shapes the cosmos silently but decisively, guiding the formation of galaxies and the web-like structure of the universe. Dark matter does not emit, absorb, or reflect electromagnetic radiation, making it effectively invisible. Yet, its gravitational pull is unmistakable. It acts as the cosmic scaffolding on which ordinary matter clings, allowing gas and dust to collapse and ignite stars. Without dark matter, galaxies as we know them would never have formed. The cosmic microwave background holds subtle clues about dark matter's presence. The tiny temperature fluctuations or anisotropies captured in the CMB maps are influenced by the distribution of both normal and dark matter. Dark matter's gravity affects how these fluctuations grow over time. During the early universe, before recombination, dark matter was already beginning to clump together under gravity. Unlike ordinary matter, it did not interact with photons and was free to collapse into dense regions. These dark matter clumps formed gravitational wells, creating potential valleys that ordinary matter would later fall into once free from the photon. Pressure. The influence of dark matter is visible in the acoustic peaks of the CMB power spectrum. The heights and positions of these peaks reflect the relative amounts of ordinary and dark matter, helping cosmologists measure their proportions with remarkable precision. Moreover, dark matter played a crucial role in the growth of cosmic structures. After recombination, as photons decoupled and the universe became transparent, ordinary matter began to fall into the gravitational wells shaped by dark matter. This process laid the groundwork for the formation of stars, galaxies, and clusters. The presence of dark matter also helps explain why the universe's expansion is accelerating in combination with dark energy. Although distinct from dark energy, dark matter's gravitational pull shapes the overall dynamics of cosmic evolution. Despite its importance, the true nature of dark matter remains one of the biggest mysteries in physics. Various candidates from weakly interacting massive particles, WIMPs, to ixions and sterile neutrinos, but none have yet been directly detected. The cosmic microwave background offers a unique window into this invisible realm. By analyzing its patterns and comparing them with theoretical models, researchers refine their understanding of dark matter's properties and behavior. Dark matter's silent influence echoes through the ancient light, a reminder that much of the universe's makeup remains hidden yet fundamental. The CMB is our guide to this unseen world, helping us unravel the invisible threads that bind the cosmos together in this way. The cosmic microwave background is not only a messenger from the early universe, but a beacon illuminating the dark, unseen forces that govern cosmic destiny. Chapter 12. Reading the curvature of the cosmos. One of the fundamental questions cosmologists have sought to answer is about the shape or geometry of the universe. Is space flat like a sheet of paper, curved like the surface of a sphere, or shaped like a saddle with negative curvature? The answer lies hidden in the cosmic microwave background, which acts as a cosmic ruler, helping scientists measure the universe's curvature with remarkable precision. The concept of curvature in cosmology refers to how space bends on the largest scales. A flat universe means that parallel lines will never meet, and the angles of a triangle add up to exactly 180 degrees. A positively curved universe, like a sphere, means that parallel lines eventually converge and triangle angles add up to more than 180 degrees. Conversely, a negatively curved universe, like a saddle, means parallel lines diverge and triangle angles sum to less than 180 degrees. The CMB's tiny temperature fluctuations provide clues about this geometry. When sound waves rippled through the primordial plasma before recombination, they created regions of compression and rarefaction. The characteristic size of these features can be predicted precisely by observing the angular size of the first acoustic peak in the CMB power spectrum. Cosmologists determine how much the path of light has been bent by the shape of space. If the universe were curved positively, these features would appear larger than expected, like looking at a distant object through a magnifying glass. If negatively curved, they would appear smaller, as if seen through a distorting lens. But measurements from satellites such as WMAP and Planck show that the universe's geometry is incredibly close to flat. This flatness has deep implications. It supports the theory of cosmic inflation, which predicts that the rapid expansion in the earliest moments would have stretched any initial curvature to near zero, making the universe appear flat on large scales. A flat universe also fits with observations of how matter clusters and how the universe expands. But even though space is flat, the universe can still have a rich and complex structure, shaped by the interplay of matter, energy, and the mysterious dark components. Determining curvature is not just a geometric exercise. It affects the fate of the cosmos. A positively curved universe would eventually stop expanding and recollapse. A negatively curved or flat universe may expand forever, but the details depend on the balance of dark energy and matter. The cosmic microwave background thus acts as a cosmic yardstick, letting us measure the shape of the vast cosmos. Remarkable testament to how light, born shortly after time began, can illuminate questions about the very fabric of space. Through this ancient glow, we glimpse the contours of the universe itself. Understanding that the space we inhabit is neither simple nor arbitrary, but precisely shaped by cosmic history. Chapter 13. The Universe's Composition Revealed. The Cosmic Microwave. Background is not just a snapshot of the infant universe. It is a cosmic ledger, recording the precise makeup of everything that exists. By studying its subtle fluctuations and spectral properties, scientists have been able to unravel the fundamental ingredients that compose our universe. From the ordinary matter that forms stars and planets to the mysterious dark matter and dark energy that dominate cosmic dynamics. Ordinary matter, or baryonic matter, makes up only about 5% of the universe's total mass energy. This includes atoms, gas, dust, and all visible structures. The CMB reveals this fraction through the characteristic acoustic peaks, where the interaction between photons and baryons before recombination imprinted telltale patterns, a much larger component. Roughly 27% is dark matter, elusive form that does not emit or absorb light, but exerts gravitational influence. Its presence is indirectly confirmed through the CMB's anisotropies and the large-scale structure of galaxies. Dark matter acts as the scaffolding for cosmic evolution, guiding the formation of galaxies and clusters. Most surprising of all is dark energy, accounting for about 68% of the cosmos. This mysterious force drives the accelerated expansion of the universe, counteracting gravity on the largest scales. Although it doesn't leave a direct imprint on the CMB, its effects influence the universe's geometry and the growth of cosmic structures, which can be inferred from precise CMB observations. together. These components form a cosmic recipe, revealing a universe that is mostly dark and invisible to traditional astronomy. The CMB serves as the foundational evidence for this model, enabling scientists to test and refine cosmological theories with extraordinary precision. Studying the CMB is like reading the universe's birth certificate, listing its ingredients, proportions, and the rules that govern their interplay. It tells a story of a cosmos that is both simple in its composition, yet is profoundly mysterious in its behavior. As we continue to probe this ancient light, we deepen our understanding of not only what the universe is made of, but how these components shape its past, present, and future. Chapter 14. Mapping. The early universe. One of the most remarkable achievements in modern cosmology has been the creation of detailed maps of the cosmic microwave. Background maps that reveal the universe's earliest structures with astonishing clarity. These celestial cartographies provide a window into the conditions prevailing just hundreds of thousands of years after the Big Bang, allowing us to trace the primordial fluctuations that gave rise to all cosmic structures. Creating these maps was no simple task. The CMB is a faint microwave glow about 13 billion years old, permeating the entire sky with nearly uniform intensity. Detecting tiny variations in its temperature and isotropies of only a few parts in 100,000 requires instruments of extraordinary sensitivity and precision. Early attempts, such as those by the COBE satellite in the late 1980s, revealed the first hint of these anisotropies, confirming the Big Bang Theory's prediction that the early universe was not perfectly smooth. COBE's findings opened the door for a new era of precision cosmology. But its resolution was limited to large angular scales. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, revolutionized CMB mapping with higher resolution and sensitivity. WMAP's data offered a full sky view at finer angular scales, revealing a complex pattern of hot and cold spots. These patterns correspond to regions of slightly varying density, representing the initial seeds of galaxies and clusters. Later, the Planck satellite took this mapping to even greater detail. Its instruments scanned the sky across multiple frequencies, separating the primordial CMB signal from foreground noise, such as galactic dust and synchrotron radiation. Planck's maps are the most detailed ever made, offering a high-definition blueprint of the infant universe. These maps are not just pretty pictures, they are rich scientific tools. By analyzing the size, shape, and distribution of the temperature fluctuations, cosmologists extract key information about the universe's composition, geometry, and evolution. For instance, the angular scale of the first acoustic peak tells us about the universe's flatness, while the relative heights of subsequent peaks reveal the proportions of baryonic and dark matter. Moreover, mapping the CMB polarization adds a new dimension, revealing information about the early universe's velocity fields and potential gravitational waves. Polarization maps help distinguish between different inflationary models and constrain the epoch of reionization. When the first stars began to shine, these comprehensive maps allow us to reconstruct the timeline of cosmic history. From the smooth plasma of the early universe to the intricate cosmic web of galaxies and voids observed today. They also provide a testing ground for new physics, such as neutrino masses and the nature of dark energy. Mapping the early universe through the CMB is like creating a cosmic archaeological record, preserving evidence of the universe's infancy and guiding us toward deeper understanding. Each pixel in these maps tells a story of quantum fluctuations magnified by inflation, acoustic oscillations in a primordial plasma, and the delicate dance of matter and radiation that set the stage for all cosmic structure as technology advances. Future missions promise even more precise maps, potentially uncovering subtle features that could revolutionize our understanding of the cosmos. The pursuit of these maps is a testament to humanity's quest to chart the unknown and illuminate the dawn of everything. Chapter 15: The Reionization Epoch. Light returns to the cosmos after the universe's birth, and the era of recombination when electrons and protons combine to form neutral atoms, and light was finally set free. The cosmos entered a long period known as the Cosmic Dark Ages. During this time, the universe was filled with neutral hydrogen gas and darkness, as no stars or galaxies had yet ignited to light up the cosmos. But this darkness was not eternal. Roughly a few 100 million years after recombination, the first stars and galaxies began to form, bringing the first sources of light and ionizing radiation. This period, called the Epoch of Reionization, marks a crucial turning point in cosmic history, when the universe transformed from dark and neutral to bright and ionized once again. The reionization process involved intense ultraviolet radiation emitted by the first generation of stars, quasars, and galaxies. This energetic radiation gradually reionized the neutral hydrogen gas, stripping electrons from protons and transforming the intergalactic medium into a plasma once more. This epoch is key to understanding how the first luminous objects shaped the cosmos. The timeline and duration of reionization carry profound implications for galaxy formation and evolution, as well as the large-scale structure of the universe. Evidence of reionization is not only indirect but also embedded in the cosmic microwave background. As the CMB photons journey across the universe, some scatter off the free electrons produced during reionization. This scattering leaves a subtle imprint on the polarization of the CMB, providing clues about the timing and extent of this transformative era. Measuring the reionization epoch is challenging, but combined observations from CMB data, distant quasars, and galaxy surveys have helped narrow down its duration, likely spanning from about 400 million to 1 billion years after the Big Bang. Reionization not only altered the state of the intergalactic medium, but also influenced the growth of cosmic structures. The newly ionized gas affected cooling processes essential for star formation, while energetic photons drove winds and feedback mechanisms shaping galaxy environments. Understanding reionization remains a frontier in cosmology. Upcoming observatories like the James Webb Space Telescope and new 21-centimeter hydrogen line experiments promise to unveil more details about this epoch, mapping the birth of the first stars and galaxies in unprecedented detail. The reionization epoch is a cosmic dawn, a moment when the universe was reborn from darkness into light, setting the stage for all cosmic evolution that followed. It reminds us that the universe's history is a dynamic tale of transformation, illuminated by the first sparks of starlight, through the faint whispers imprinted on the cosmic microwave background and the light of the earliest galaxies. We continue to unravel this vital chapter in the story of everything. Chapter 16: The Integrated Sachs-Wolf Effect. Gravity's imprint on light. As photons from the cosmic microwave background journey across the vast expanse of the universe, they do not travel through an empty void. Instead, they navigate complex cosmic landscape shaped by clusters of galaxies, vast voids, and the mysterious forces of gravity. One subtle but profound phenomenon that arises from this journey is known as the Integrated Sachs-Wolf (ISW) effect, a gravitational imprint left on the ancient light by the evolving structure of the cosmos. The ISW effect occurs because the gravitational potential wells and Hills regions of higher or lower mass density change over time as the universe expands and evolves. In a universe dominated solely by matter, these potentials would remain constant. But the presence of dark energy causes the expansion of space to accelerate, leading to a decay of these gravitational potentials. When a photon passes through a gravitational well, region of space where gravity is strong, it gains energy, falling in, and loses energy climbing out. If the gravitational potential remains unchanged, these energy shifts cancel out. But if the potential evolves during the photon's passage, a net energy change occurs, altering the photon's temperature. This effect adds subtle temperature fluctuations to the cosmic microwave background, particularly on large angular scales. Detecting the ASW effect requires correlating CMB maps with surveys of the large-scale structure, like galaxy distributions and clusters, to identify where gravitational potentials are changing. The discovery and measurement of the ISW effect provide powerful evidence for dark energy's existence and its influence on cosmic expansion. It complements other cosmological probes, confirming that the universe's growth and geometry are shaped not just by matter, but also by this enigmatic, repulsive force. Studying the ISW effect helps scientists understand how the cosmic web, the vast network of galaxies and voids, evolves over time. It also offers a unique way to probe the properties of dark energy, constraining its density and equation of state. Moreover, the ISW effect demonstrates how gravity, one of the universe's fundamental forces, leaves its mark on light itself, weaving a connection between the fabric of space-time and the photons that carry ancient stories. Through this gravitational fingerprint, the cosmic microwave background becomes not just a relic of the past, but an active participant in the universe's ongoing evolution, a glowing messenger shaped by the forces that govern all cosmic destiny. Chapter 17. Secondary Anisotropies. The universe's later imprints. While the primary anisotropies of the cosmic microwave background reveal the universe's earliest fluctuations, the journey of these ancient photons through cosmic time has left additional marks known as secondary anisotropies, which tell stories of the universe's evolving structure and the interactions of light with matter long after recombination. Secondary anisotropies arise as CMB photons encounter various cosmic structures, clusters of galaxies, hot gas, moving masses, and large-scale gravitational potentials. These interactions subtly alter the photon's energy and direction, imprinting new features onto the CMB map. One key secondary effect is the Sunyaev-Seldovich SZ effect, where CMB photons scatter off high-energy electrons in hot gas within galaxy clusters. This scattering boosts photon energies, creating characteristic distortions in the CMB's spectrum, and allowing astronomers to detect and study galaxy clusters across vast distances. Another is the Rees-Schoma effect, caused by time evolving gravitational potentials in large-scale structures. Unlike the ISW effect, which operates on large scales due to dark energy's influence, the Rees-Schoma effect arises from nonlinear growth of structures and can leave localized imprints. The gravitational lensing of the CMB also counts as a secondary anisotropy. As photons pass near massive objects, their paths bend, distorting the observed CMB patterns. This lensing effect not only blurs the primordial anisotropies, but also creates new non-Gaussian features, helping researchers map the distribution of dark matter in the universe. Secondary anisotropies provide a complementary window into cosmic evolution. They reveal how the universe's large-scale structures grew and evolved, how baryonic matter interacted with radiation, and how the interplay of forces shaped the cosmos after the first light was released. Studying these later imprints requires sensitive measurements and sophisticated analysis, disentangling primary signals from secondary contributions. Yet, these efforts enrich our understanding of the universe's history, filling in the chapters between recombination and the present day. In this way, the cosmic microwave background is not merely a relic frozen in time. It is a dynamic canvas, continually altered by the universe's evolving content and structure. Each secondary anisotropy adds a brushstroke to the cosmic masterpiece, narrating the complex interplay of matter, energy, and gravity. Through these subtle, later imprints, we glimpse not only the dawn of the universe, but its unfolding Storia universe in motion, forever shaping and reshaping the light that connects us to the very beginning. Chapter 18: The Cosmic Neutrino Background. Ghosts of the early universe, beyond the photons that form the cosmic microwave background. The early universe also produced another elusive relic, a sea of cosmic neutrinos. These nearly massless, weakly interacting particles permeate space, forming the cosmic neutrino background, CNB. Ghostly messengers from the universe's first seconds. Neutrinos are fundamental particles that rarely interact with matter, passing through planets, stars, and even entire galaxies almost undisturbed, created abundantly in the hot, dense conditions shortly after the Big Bang. These neutrinos decoupled from other matter even earlier than photons. Roughly 1 second after the Big Bang, the cosmic neutrino background carries unique information about the universe's earliest moments and the processes governing particle physics at energies unreachable in laboratories. Though never directly detected, its existence is strongly supported by cosmological models and indirect observations. The presence of the CMB affects the universe's expansion rate and influences the formation of cosmic structures. It leaves subtle fingerprints in the cosmic microwave backgrounds, anisotropies, and in the distribution of galaxies. Precise measurements of these effects help constrain neutrino masses and properties. Detecting the CMB directly remains a formidable challenge. Neutrinos interact so weakly that current detectors cannot yet measure this background. But future technologies and experiments may bring this ghostly relic within reach. The cosmic neutrino background reminds us that the universe's story is written not only in light, but in particles invisible to our senses, carrying whispers from the dawn of time. These ancient neutrinos are silent witnesses to the universe's birth, preserving secrets of fundamental physics and cosmic evolution. As we continue to study the CMB and the broader cosmic landscape, the CMB stands as a profound frontier, invitation to explore the invisible and deepen our understanding of the universe's most elusive components. Chapter 19. Testing Fundamental Physics with the CMB. The Cosmic Microwave. Background is not only a snapshot of the universe's infancy, but also a powerful laboratory for testing the fundamental laws of physics. Embedded within its subtle fluctuations and patterns lie clues that challenge and refine our understanding of particles, forces, and the fabric of space-time itself. By analyzing the temperature, anisotropies, and polarization of the CMB, scientists can probe conditions at energy scales far beyond those achievable in terrestrial laboratories. These measurements place stringent limits on models of particle physics, such as the number of neutrino species, the mass of neutrinos, and potential interactions beyond the standard model. The CMB also offers a unique window into the nature of dark matter and dark energy, mysterious components that dominate the cosmos but remain poorly understood. Through precise mapping of the CMB, cosmologists can constrain the properties of dark matter candidates and test hypotheses about dark energy's equation of state, shedding light on their origins and effects. Another fundamental test involves the search for primordial gravitational waves in space-time, generated during the universe's rapid inflationary phase. Detecting their signature in the CMB's B mode. Polarization would provide direct evidence of inflation and open new horizons in quantum gravity. The CMB also helps test the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. Anomalies such as the cold spot and alignments in the CMB challenge this principle, inviting alternative explanations and deeper scrutiny. Moreover, the CMB constrains theories about the early universe's physics, including phase transitions, topological defects, and exotic particles. These investigations push the boundaries of cosmology and particle physics, bridging the two fields in a grand quest to understand the cosmos in essence. The cosmic microwave background is a cosmic laboratory where the universe tests itself, offering data that refine our physical theories and inspire new ideas. Through its ancient light, we glimpse not only the past, but also the fundamental workings of reality. Chapter 20: The Legacy of the Cosmic Microwave. Background. The cosmic microwave background stands as one of humanity's greatest scientific discoveries, a faint whisper from the dawn of time that has forever transformed our understanding of the universe. Its legacy extends far beyond the realm of cosmology, touching upon philosophy, technology, and our place in the cosmos. From the accidental discovery by Penzias and Wilson in 1965 to the sophisticated satellite missions of COBE, WMAP, and Planck, the CMB has guided scientists on a journey across billions of years. It has provided a detailed map of the infant universe, revealed the composition of cosmic ingredients, and tested fundamental physics in ways once thought impossible. The CMB's legacy is a testament to human curiosity and ingenuity. It shows how careful observation, innovative technology, and creative theory can unravel the deepest mysteries of existence. Through its ancient photons, we connect with the universe's birth, witnessing events that occurred over 13 billion years ago. Moreover, the CMB has opened new fields of research, inspiring generations of scientists to explore the cosmos with ever greater precision. It has driven technological advances in detectors, data analysis, and space missions, with benefits that extend to other areas of science and industry. Philosophically, the CMB invites us to contemplate the vastness of Konka, the vastness of time and space, the nature of reality, and our place in an ever-expanding cosmos. It reminds us that the universe is a dynamic, evolving tapestry, and that we are participants in its ongoing story as new experiments probe deeper, searching for elusive signals like primordial gravitational waves and the cosmic neutrino background. The legacy of the CMB continues to grow. It serves as a foundation for future discoveries, a beacon illuminating the path toward understanding the ultimate origins and fate of the universe. In embracing the cosmic microwave background, humanity embraces the cosmos itself, profound legacy of knowledge, wonder, and the enduring quest to uncover the secrets of everything.